Hi everyone. I think we're connected. I'm hoping everyone can hear me okay. Uh, welcome everyone. Welcome to this evening's presentation. Just to give you a little bit of an introduction, I'm Tom Scaramuzza, so I am the current chair for the IMechE Milton Keynes Railway Division. And we're joined by two speakers tonight who I'll present just in a couple of minutes. So first of all, thank you. Thank you for joining us. These are strange times. It's the first time we do an event virtually. So I hope all the technology works and I hope you enjoy this evening and find it really interesting. So we've got two speakers this evening. We've got Simon Jarrett from Chiltern Railways. We've got Dr Durazo Cardenas from Cranfield University, who are going to be covering two different areas of robotics and just how it's impacting them and the work they're doing on the railways. So you do have the ability to ask questions. If I could ask you to hold your question, if you want to ask questions throughout, by all means do so. What I will say is we will be answering them towards the end. And that's just helped with the flow of the presentations. I know there's quite a few people on, which is great news for us. What that does mean, however, is if we do have a lot of questions, I may group some, I may just pick some, just in the interest of time and making sure that we finish on time. So without any further ado, I'd like to introduce my first speaker, who is Simon Jarrett.
Thank you, Thomas. Hello. Good evening, my name is Simon Jarrett. I'm the Engineering Assurance and Development Manager for Chiltern Railways. So I'm involved in the day-to-day operation and maintenance of rail vehicles. I don't know a lot about robotics, so I'm not a roboticist, but I'll be talking today about the work that we've been doing with various academic and other partners on the application of robotics to rail vehicle maintenance. A bit of background: back in 2016, RSSB, the Railway Safety and Standards Board in the UK, asked academia and industry to consider the application of robotics to rail vehicle maintenance. This was my start of involvement. I actually thought at the time they were mad, but have become convinced over the years that robotics has real application to our industry and to our future. So why on earth would we want to use robotics in rail vehicle maintenance? Well, robotics, we're aware, has been used in manufacturing for over 40 years. But its application in maintenance environments is actually fairly rare, except in very hazardous environments such as offshore. But what we are finding as an industry, and certainly it's our experience, is that we expect our fleets to grow in the next 20 years. But we are finding that land availability for new facilities is becoming difficult to find. And so what we're having to do is work out ways of using our depots more efficiently to maintain more vehicles. At the same time, we are finding that actually it's becoming more difficult to recruit and retain staff. If you looked around most UK train depots, most of the staff are in their 40s or 50s. And actually with things like Brexit, we're actually finding it's becoming more difficult to recruit and retain staff. So robotics offers an opportunity to get the work done on the vehicles, but without increasing staff numbers. In fact, when I talk to my 12 and 14-year-old sons, and I talk to them about rail vehicle maintenance, I say we do most of the work at night, and sometimes in the cold, in the snow, and in the wind and the rain. Do you think that's something you'd want to do when you grow up? I tend to get the answer no. They tend to prefer to sit and think about a career on their iPad. We expect and hope that post-COVID, rail vehicle ridership will recover and increase, and certainly to meet our current ambitious climate change targets, we would expect further global modal transfer of people onto the rail network. Our environmental issues will remain. So what are where might we use robotics? In terms of where I think they're most applicable, it's going to be tasks that one might describe as dull, dirty, difficult to do, dangerous and frequent. So examples might be cleaning. It's not particularly dangerous, but it requires lots of labour. For particularly on mainline passenger vehicles, there's lots of fluids involved. So toilets require fluids, water, and we also need to empty them. On a diesel vehicle like my own that we operate, we have to top up and use top up diesel fuel fairly frequently. But also things like replacing brake pads or brake blocks, and working on high voltage equipment such as shoe gear and pantographs. Stuff that is done frequently presents a better business case to develop for robotics, and that's where we've targeted our work. But dangerous tasks, for example, things like working on pantographs involve both working at height and on high voltage, potentially high voltage electrical systems. So they are using so by getting a robot to do that, we eliminate the exposure of human beings to those hazards. So back in 2016, RSSB commissioned 3 academic feasibility studies on the use of robotics in rail vehicle maintenance. The first one was between Brunel University and ourselves, and that was about the application of robotic fluids, and I'll go on to talk about that later. The second one was with Cranfield and Jarrett universities, and also with ourselves and Bombardier, to look at the application of robotics to cab front cleaning, and I'll talk a bit about that in a moment. The third study, which I won't discuss too much, was with Birmingham University and I think Southern Railway, and looked at the application of additive manufacturing to railway wheel sets. The basic idea was to have a wheel set that was fitted to a train, and rather than use up the wheel set life, what you would do is you would build up, as the wheel tread was used up, you would then effectively spray new metal onto the wheel set to rebuild it back up, so you effectively had an infinite life wheel set. It was a really good idea, but sadly fell down when they started to think about metallurgy. Because if you think about a railway wheel set, it's the forged item, and it also has some fairly strong heat treatment on the wheel tread. And trying to replicate those features with 3D printing is not yet possible. That's not to say that in the future it won't be possible. So I'm now going to go on to talk about cab front cleaning. So you'll see on the top right hand picture an image of how we currently clean train cabs. So why on earth is this important? You're probably wondering. You may be wondering. Well, actually, first impressions count. So when our trains turn up at the station, the first thing our passengers see is the front of the train cab, and that presents a good impression. Either it's dirty and mucky and they just think, they haven't bothered maintaining or cleaning this train, or it's nice and clean. It presents a good first impression to us, for our passengers. But also, what we have found over the years is that our passengers relate how clean the train is as to how well we maintain it. They don't have any other measure for how well we maintain it except generally how clean it is. So if they get that good first impression, they will think and have the impression that we maintain it well, which of course we do. So what happened in this study is we looked at how we currently manually clean trains, and then we built at Cranfield a 1/8 scale model of how we might use a robot to clean a train. It has to be said, actually, whilst cab cleaning looks fairly innocuous and fairly unrisky, actually, if you think about in an electrified railway environment with 25,000 volts above you, or third rail at 750 volts, having lots of water about can present an interesting hazard. So actually getting a robot to do this task eliminates a lot of risk. Also, as we said, that our cleaners aren't great at cleaning the top of the train. As you'll see from that picture, they find it difficult to reach the top. So, moving on, the current slide you'll see is the 1/8 model. And if I press that, you'll start to see it's based on a well-known UK train that you may see on the cross-country network, for example. And you'll see how Cranfield developed a cleaning head that would potentially clean the front of a train. The cleaning head, or end effector in robotics language, is actually quite a complex piece of kit. It has to include and dispense both water and detergent, and also have pressure sensors, because we don't want to damage or apply too much force on the front of the cab, or also knock things like and damage things like windscreen washers, which could be anywhere on that cab windscreen front. But it's difficult to, so the discontinuities make it actually quite a difficult challenge, but Cranfield and Harriet Watt together managed to produce a control system that would potentially do this. So now what's happening is this is being taken forward by a company called Garandale through a knowledge transfer partnership, and they're developing this technology. They have a business that builds train washers to clean the sides of trains and the roofs, and they see this as a complementary offering to what they can do. So we should see train front and end vehicle cleaning robots available soon, I would hope. Right, so I'm now going to move on and talk about a thing that I find a much more interesting project, or it's much more relevant to where our business is, and that's how to replenish and remove fluids from trains, which as a diesel train operator is of particular interest to us at Chiltern Railways. So mainline trains require frequent daily or sometimes daily fluid replenishment, and that's things like fuel, oil for engines, fresh water for toilets, but also then removing the toilet and effluent and topping up things like sand and windscreen wiper fluid. This is applicable to both diesel and electric trains. So electric trains have most of these fluids, but obviously don't have the diesel fluid. For us as a particular diesel operator, a significant labour requirement and there's a lot of depot capacity is used up just doing these tasks, and there are some health and safety hazards exposure. We fuel our trains typically every 2 to 3 days. So the academic feasibility study between ourselves and Brunel looked at how we currently do this, and then looked at design requirements for what a robot would need to do to replicate those tasks, and then developed concept ideas and a business case for a Apologies, I've jumped 2 slides, I'm just going to jump back. So what you can see on the screen now are 2 potential concepts that were developed by Brunel. The one on the left, we have a robot that operates on a rail, of course, and moves back and forth to the various ports on the side of the train to attach to different hose types. On the right-hand side of your screen, you'll see a second concept whereby we have different hoses and kind of fluids, each with their individual robot, and they move in and apply all at the same time to the train. So typically when we do these types of tasks, we have one person and he walks along the side of the train applying the different hoses and fluids to the train. And typically we spend 30 minutes per train doing these routine tasks. When we evaluated it through a robotic autonomous solution, or a RAS, we concluded that we could probably do that in 7 minutes. Our main limiting factor is actually the dispense rate for the fuel in this case. So that was the concept work with Brunel. We then bid for some further funding with a company called TBG Solutions and Brunel to develop the concept further and start to test some of the ideas. And what you can see at the bottom of the screen is a more developed version of a robotic servicing robot for fluids. So the robot moves along on a rail connected to a series of reservoirs and can then interface with the train at the different fluid dispense points. What we also start to look at this point is how we would interface with the vehicle, what we call the ports. So if you have because if you think about it right now, all our ports are designed around human beings interacting with that rail vehicle to put in diesel fuel or put in water. And those port designs may not be as easy for a robot to use. And what we did was we constructed, as you can see on your next slide, a test rig. So what you can see here is a body side image of a train with the great Isengard Kingdom Brunel, of course, sat in the window looking out. And then we have our robot here that slides on a slider with the various attachment points moving in and out. Unfortunately, this image or photo was at a much earlier stage of the build. It's much more advanced now, and actually there is a link to a YouTube video that's hopefully available that shows the complete robot in action, attaching and detaching to the train and then applying dummy fluids. So about 18 months ago we demonstrated this to various industry stakeholders like RSSB, the Department of Transport, and various new train builders, and got very good feedback, I have to say. But that is largely where that project's got to. So I think what we've got to is the point where the technology we've managed to demonstrate, but we now need to take it further, industrialise it, and demonstrate it on a proper train and in a proper depot. So where are we going with this? Well, our vision is to develop a robot servicing road. For those of you not familiar with depots, we actually divide these spaces up where we park the trains into what we call roads. So our aim is to develop a road that does a number of different tasks all at the same time. I think we will start off with the tasks we've already worked on, such as cab, front and body end cleaning. and also look at fluid servicing, because we've done quite a bit of development work in those areas. But we will also then start to look at the automatic inspection of brake pads, wheels, underframe equipment, where there is some technology that's already quite well developed. But then take that a step further, and for example, when you inspect the brake pad, develop the technology to replace it if it's worn. Similarly, on the shoe gear and on the pantographs, if you've got a worn shoe or a worn pantograph carbon, develop the technology in the robot to change those elements. This would release, once it's developed and proven, a lot of additional depot capacity as we roll out across depots in the UK and probably internationally. But as we said, that we would probably have to make some changes to components that we fit to train to make them more suitable for a robot to work on. So currently, when we change a brake pad, our human being who does it, he pushes it up into a slot and waits to hear and feel for a click. We're trying to get a robot and train it to hear that click and have a feel for that would be quite a difficult task. But if we had a more mechanical means of securing it, combined with a lot of the existing photo and digital analysis technology, you could prove that the brake pad was fitted and was secure. I am also interested in looking at how we can do interior train cleaning, although I actually think it's a much more difficult task for a robot to do. But actually, it's the most frequent maintenance activity we do to a train. So our vision is to focus on these frequent activities and start to develop them for robots. As we said, there will always be a need for a human being to maintain a train. I don't think a robot will ever be able to do all the maintenance, because there are some tasks that we do very infrequently or require skills only human beings currently have. So, in conclusion, actually, rail vehicles are remarkably well suited to robotic maintenance. If you think about it, my train only operates in one dimension. And we have the opportunity as an industry to leapfrog other industries in the application of robotics to maintenance in particular. We've done a lot of early concept work now on the dull, dirty, frequent maintenance tasks, and now looking to develop those further. I have to say that we've struggled so far because probably the next stage requires a few £1 million to really develop and demonstrate the technology and how we test it. But we also need to bear in mind that we may need to consider changes to trains and standards, so they are better able for a robot to maintain them. So our next stage, and we are talking to large manufacturers who do a lot of the maintenance in the UK, is to start to develop ideas to build much larger prototypes. And we are also sponsoring through Cranfield PhD studentships to develop the ideas and the technology further. And my final slide, I'd just like to recognise those who've contributed towards what we've done so far. So TGB Solutions, Garendales, and Brunel, and also Cranfield. Thank you very much for listening. If you've got any questions, I look forward to answering them later. So I'm now going to hand over to Isidro to talk about his work he's been doing on the application of robotics to rail infrastructure maintenance.
Thank you. Good evening. Let's see. Okay. Welcome to this presentation about robotics in rail infrastructure maintenance. My name is Isidro. I'll take a few seconds to introduce myself. I'm a lecturer at the True Life Engineering Services Institute at Cranfield. What we do in this institute is we work with long life assets of higher value, assets that may last for a very large number of years, and typically are some of the critical national infrastructure of the country. So some of the areas that I work on is autonomous systems, NDT systems, maintenance systems, design in technology readiness level management. I also feel necessary to introduce a little bit Cranfield, because I realize maybe not everybody knows about it. We are a university, a wholly postgraduate university. That means that we don't have undergraduates, we only have Master of Science students and PhD students. So it's a very research-intensive institution. So depending where you look at on the day or the year, but we top World 40. We are considered number one for UK research income from industry per academic. We've been in the news recently because we do have a number of research areas that made the news. For example, we have an autonomous vehicle that's been out and about. We have also a new control tower that's entirely digital because we have our own airport as well, and we have a couple of aircraft too. So I'll move on from introductions to get into what the presentation is today. So the contents I'll cover is work that we're doing on behalf of Network Rail for the Shift to Rail program, that is the rail inspect and repair system. I'll briefly introduce the concept of this system. I'll show you, or I'll try to demonstrate the progress to date using an illustration of technology level transitions. So I'm going from concept formulation to demonstration in operational environment. I will also talk about some of the challenges that we face, and I will also show a bit of work that we're doing in terms of NDT demonstrations. And finally, I will conclude my presentation with an overview of the Autonom project. So, of the work that I'll be presenting today, I have to say that the vast majority of it has been funded through the European Union and the diverse couple of projects that they have, which is Shift to Rail. And on the Shift to Rail, we have Into Smart and Into Track, supported by Network Rail. And in the last case of the last project is EPSRC as well as Network Rail. So these are the primary sponsors of the work that I'll be showing today. So a brief introduction to the rail inspect and repair system, the concept. So obviously the motivation, as Simon has pointed out, is to do with in rail infrastructure is to do with enhancing the network utilization. So how many trains more can we put in the network, safely put in the network? And also a great factor in this is the safety of network rail staff. As Simon pointed out, maintenance staff has to go sometimes late at evening, late at night, and work in hazardous conditions. So this is a positive step towards also the health and safety of staff. Also, this concept can save significant time, and that is because with the capability not only inspecting but actually repairing and coming back to inspect and send message back to base to say it's all done. Obviously, that saves a lot of time as opposed to sending a new measuring train, finding a fault, and sending a crew to verify the defect, and then sending someone else to repair and someone else to verify that the fault has been repaired. The fundamental technology requirements of this concept are modularity, and that means that different platforms for inspection and repair could be used. We're talking about sort of fairly generic architecture within the system so that it accommodates different inspection and repair systems. And another principle that's fundamental to this is agnostic. So that means that, again, the architecture is flexible enough to allow different types of vehicles. The whole of this concept it relies on systems engineering. So for those that work with systems engineering, you recognize the V model to the right. That illustration is just therefore illustrate the principle of the work and how comprehensive the development has been since the development of the concept all the way to capturing requirements and producing the concept and field demonstrators that need validating. Another fundamental technology requirement is slow network utilization, and that means that the vehicles should be able to come in the network very quickly, go out of the network, so the more trains could be put in place, as opposed to using a lot of time of the network for maintenance. So our keys here in the development and implementation of this technology. Obviously, the rail is a safety regulated environment, and there are many risks that need to be managed. And from the implementation side, all infrastructure assets must comply with network rail procedures, and this involves product acceptance, design for reliability. So there is a long list of requirements that must be satisfied before a product is put into deployment phase. So I've listed here the technology.
Okay, I think we might have just lost Isidro. We'll see if we can get him back quickly. Just bear with us. Sorry about this.
Readiness levels.
Hi everyone, it's Tom here. We appear to have a few problems with Isidro's connection. We're just trying to get him back on. We'll try and do this as quickly as possible. So if you can just bear with us, that'll be great. Thanks and sorry about this. Okay, right. Well, whilst we try and get Isidro back, what I might do, Simon, is I might start asking you a few questions if that's okay.
Yeah, that's fine.
Um, so I'm just loading them up now. Right, so our first one's from Andrew Starr from Cranfield, who's saying, Simon, how did you get on with safety cases? Autonomy still seems to be outside of the current rule set, and how did staff respond? What does consultation with the unions bring up?
Right, I'll just take some notes.
Yep, no
So,
problem.
in terms of safety cases, I have to say that we haven't really started to develop those yet. But it will be something that we need to do. One of the things to note is that railway depots are largely regulated as kind of industrial facilities. Whilst they fall into the rail category, they tend to be managed more as industrial facilities. One of the things we have found is that actually robotic technology is remarkably good at being safe, partly because of 40 years experience in car manufacturing, and particularly collaborative robots that sense people working in and around them achieve a very high level of safety. So what that happens is that a robot will work, it senses somebody near to them, it will stop moving, and then once the person walks away from the robot, it then continues working. Personally, I don't perceive. I think when we first do it in a real live depot, there will be some staff safety concerns, but I don't actually perceive that once the technology in action and experience it, that they'll get used to it quite quickly and feel quite confident and safe walking around it. But having said that, in terms of safety, we will have to apply what's called the CSM, or the Common Safety Method process, that applies to changes to the railways to demonstrate that it's safe to operate. In terms of consultation with staff, we haven't really done that yet. We haven't had a project yet where right now we're only looking to kind of demonstrate and develop the technology, but there will be a stage when we start to bring it to actual depots, and we'll need to consult with staff about it. Do I perceive there will be issues? There may be, or there's bound to be. But I think if we say to staff, look, what we're doing is we're taking away those tasks that you find the most dullest, boring tasks to do, and we can therefore use your skills on the more interesting tasks that you like doing. I think that's a way to sell it to staff. So I think, Thomas, is that satisfactory?
Yeah, that's great. No, thanks for that. Thanks for that, Simon. Right, I've got a second question from Andy Batters. Hi, Andy. So he's asking about the fluids concept and how you ensure that the train positional accuracy and alignment of the filler openings, and then how is sealing controlled to ensure no spillage or leakage of fluids.
Right. So the alignment, we expect that the robots will be equipped with effectively digital cameras that can therefore locate the interface between the robot and the train. But the good thing about a train, of course, is it only really moves in one dimension, so that aids the whole interfaces. But we would expect the robots to have cameras, fairly standard now in industrial robotics. In terms of sealing, that is an interesting area, and hence why we've been doing some work, particularly with Brunel, on the port design. So that is the interface between the train and the robot. And Brunel are quite keen to look at what the effects are of misalignment of the ports, and how we design the ports to deal with a degree of misalignment, but also maintain a high degree of sealing. Thomas, Is that okay?
Brilliant.
Okay.
Yeah, that's great. Yeah, no, thanks for that. Yeah. Right, I'm just loading up the other questions. So yeah, the box is a little bit slow, but we are getting there. So I've got a third one from Robert Cummins, who's asking, are you aware of any work going on in other parts of the world in the same area of robotics? So are there any sort of similar projects going on in similar areas that you know of?
We are aware that there are some other projects internationally looking at the application of robotics that we are aware of, but actually we haven't done a lot of work. So in Japan, where robotics are obviously quite well established, there are videos on YouTube of trains being spray painted by robots. So that's quite an interesting technology in Japan. We know that in Germany they're also looking at toilet emptying and toilet tanking or filling up. One of the stuff that actually Brunel's done for us is that they've done a patent search. So looking across internationally at patents on the applications of robotics to rail vehicle maintenance, and there are very few, if any, patents. So we think actually the UK may be a bit of a leader in this field, particularly if we can get it to the next stage and get it out and demonstrate it on actual rail vehicles in actual depots and start to make it more productive.
Brilliant. No, that's great. Thanks for that, Simon. I'm keeping an eye on the chat. I know we managed to get Isidro back in, but he seems to have dropped out again. So I do have a final question for you, which is on the use of nanotechnology for windscreen coatings. So the question was whether any form of nanotechnology for coating windscreens would make cleaning easier, i.e. sort of easier than just spraying and scrubbing, for example. Or so rather than having to do any scrubbing, you just spray directly. I don't know if that's something you've worked with at all.
There are products already available, and we actually regularly apply a particular product, and that does make cleaning the windscreens easier and cleaning the cab fronts easier. But unfortunately, flies still collide with the train front and make it dirty, and they don't fall off. There are some bits of matter that are make it much more difficult to clean the train front, particularly flies we find in spring. So the kind of the nanotechnology type products make the cab front and the train much easier to clean, but we still need to clean it.
Right. Yeah. Yeah. No, I can imagine it would only go some way to help you. But yeah, it won't be able to solve all. Okay, well, I've been through all the questions that we've got for Simon. Isidro is still having a few problems with connecting. So what I might suggest is we leave it for 5 minutes or so. I know Isidro is talking about potentially restarting his PC. It sounds like there are a few connection issues. So I don't know if people want to go and make themselves a cup of tea or a cup of coffee. And what we'll do is we'll try and reconvene at 6:20 and go from there, if that's okay with everyone. So yeah, if you want to take 5 minutes out, we will try and have everything back and running over the next 5 minutes. Hi everyone, it's Tom here again. Yeah, we're just waiting for Isidro to come back. He's having a go at restarting his computer, so hopefully that will solve any connectivity issues. When we were trying this yesterday, it all worked fine. So yeah, it's just obviously on the real thing, we've been a bit unlucky by the looks of things. But yeah, I'm just anxiously looking at the chat we've got here, just keeping an eye on that, and when he starts messaging back, then hopefully we'll be good to go. So yeah, if you could just bear with us for a couple more minutes, hopefully we'll be up and running again. So my apologies to everyone for this, but yeah, I'll give you all a shout when we're up and running again. Thank you.
Tom, I see that we have another question. So one of the committee has asked, are the manufacturers engaged in terms of train design for the use of robotic maintenance? Or is that turkeys voting for Christmas? We haven't we're starting to engage. The truth is we're starting to engage with the manufacturers and talk to them about it, but also engaging with standards bodies, because we need standards to reflect or potentially reflect the use of robotics for railway maintenance. Actually, I think it's in the best interest of manufacturers to engage with this, partly because actually they sell trains now largely not just on the purchase price of the train, but also the maintenance package that goes with it. So if the maintenance can be done in a cheaper or more efficient way, which potentially robotics enables, then that's obviously a selling point for the manufacturers. So I don't think they're voting for their turkeys voting for Christmas. I think actually there is some interest there from the manufacturers we've found.
Brilliant, thanks for that, Simon. It sounds like Isidro's dialed in on the phone. So can you hear us, Isidro?
Yes, you hear me.
Brilliant. Would you like me to drive the slides?
I think I can do it from my computer. I'll be speaking to my phone.
Okay, I'll leave you to it.
I just wanted to know how far I got.
So you got to rail inspect and repair system concepts, so a brief introduction. And then the next one you've got is talking about TRL 1 to 9.
Yes, that is what I left the presentation. I'll start here. Okay. Sorry, I see what happened. The presentation back now. Hopefully I can stay in. Yes, I mentioned previously the introduction to the concept, and point of my next slide is to illustrate that through the application or development of new technology to go through a framework generally goes to the framework of technology levels introduced by NASA, I think. So what I have here is Vision Horizon 2020. So this gates and descriptors that this technology has been adopted. Onto technology level 9 system approved and proven. We from technology 5, where we try and give illustration of what's been going on. So if we look at this illustration here, we have the just net rate levels with an arrow, frequent arrow, and I put some images in that represent what went on. So at the earliest level of the technology, the discussions take place. Then from they perform look at technologies that are available to deploy and to satisfy their required needs. It was concluded back then that they needed a new method and a new vehicle to achieve the inspect system. So the new framework was developed at technology readiness level 2, and at technology readiness level 3, we have the initial developments of the architecture, will be also known as the command and control architecture. First on, was by sound. All that is right. Just going to change microphone now. Hopefully this is better. So I've said before that the technology progresses to these levels, and initially we had the first discussions, the first ideas, workshops to develop the concept, and also a horizon scan was performed to look for technologies that were suitable in the market already for these rail inspect and repair system. So there is a journey through this, and then on the second level there was the first framework developed for this, and for the level 3 then all the architectures were developed, the requirements were captured, the system requirements, the stakeholder requirements, and that led into a software demonstrator that was produced by the technology, the transport systems category. So this more or less where Cranfield University began their involvement in this project. We developed a hardware demonstrator that's known as Evo, which is a small-scale train that does, in effect, use this technology. We were also involved in verification and validation of the first demonstrator, which was the software one. So we're currently at level 5, where we have a new vehicle, which I'll describe in a few seconds. And at this level, we're looking to test in the lab first, and then move to an environment that's representative of a rail environment, and finally move out into a test facility rail environment. So along the way, obviously, those little men in there with helmets are representing the health and safety and risk management processes that need to be in place throughout the development of the technology. To make sure that we actually achieve these levels, we've developed a tool that enables us to assess based on a number of marks and points that come from the technology readiness level scale, both from NASA and the proper rail, the rail technology readiness levels, which are more comprehensive than NASA. So move on. So one of the critical aspects of this rail inspect and repair is the architecture. And here I'm illustrating the machine state diagram. And this is quite important because it tells us what is expected of a robot in the rail inspect and repair system. So what is expected of it is to select a job, being able to select a job, and then transit to a job, position itself to being able to perform the task. And in this case, it could be a payload robot, it could be a gripper of a robot, or any other technique we decided to use for this system. In our case, it will be a robotic arm. And then to position itself near the position to execute the task. On completion of the task, the robot is ready then to select another job or return to base. So this is the essential machine state diagram that enables or describes what's the activities what are the activities that the robot needs to perform within this system. So the early developments, as I said before, were by the Transport Systems Catapult, and they produced a model. And this model demonstrated for the first time the inspection and repair technology. It used a simulation model, which was quite difficult to assemble and to make work. But they got there in the end. We conducted the V&V process, the verification and validation process. The system that they produced demonstrated the architecture, and it also made use of a large number of the stakeholders and system requirements specified for this product. But it was only a software demonstrator. So we then, Cranfield developed NEMO, which is a hardware demonstrator. And NEMO demonstrates the application of the rail and repair architecture. It uses Arduino controllers. It can perform fault search on a track. And it uses a color detection cameras to detect the simulated faults. These are movable, so we can go to exhibitions, as I showed in that image there. We are at the Ukraine conference last year, and people were able to position simulated faults along the track, and the robot will go and find them. And once the robot found them, it positioned itself to do some 3D printing using a robotic arm it has as part of the system. The NEMO is able to communicate with supervisor using Wi-Fi and a tablet to interact with the human in the loop, and then it performs recovery to base when finished, which is the machine state diagram requirements for this technology. I do have a video here, and see if I can play it, of NEMO doing or trying to describe what it does. It looks like it's not playing. NEMO is as I said, a small scale robot with a gauge of 5 inches. It does have cameras at the front, replicating a bit what the new measuring train does. And then once it's located these simulated faults, it then goes and does a 3D printing on the place of the fault. Okay, so it looks like my video won't play, so I will move on to the next slide. So for the higher technology various levels, we now have a Warthog ClearPath from the company ClearPath. This is a vehicle purchased by Network Rail, and it's currently in one of our labs. It's a fairly mid-sized robotic vehicle comes with its own robotic arm, measures about 1.5 meters in length, and it's just about the size of the gauge on the rail track in the UK. It does have a number of communication systems like Wi-Fi, Ethernet, USB, and in its hardware it comes with encoders, LiDAR, GPS, and universal robotic arm. It obviously also comes with drivers for ROS and RVs, which is the visualization system for this technology, and support for gazebo and modeling. So this will be the main vehicle used for the higher technology readiness levels. So the tasks at high level that we need to do for this vehicle, the first one is setting up, integrate the different systems, like for example the robotic arm and the command for the vehicle. We need to develop a use case, safety compliance, also as part of this, and improve functionality deployment. And we move on for the 6th level, where we actually see defects, and we command the vehicle to go where we need maybe work around obstacles and things like that. Finally, the last stage is to do with test in a test facility for rails, and demonstrating the whole capability of the vehicle, as well as conducting validation and verification processes. So some of the challenges that we face with this technology, or will be faced by network rail with this technology, is the fact that we, at the moment, don't have a procedure to go into a possession. The vehicle at this stage is, or the experiments are designed to interact with people and doing a repair in a possession. A possession is a restriction to access for rail transit when a maintenance in the infrastructure of the network is required, then services are interrupted, and there is a very strict procedure to be followed in terms of assuring safety of all people involved. And this means that no trains can go through the track during this period. As I said, this is a very strict procedure, so at the moment it doesn't take into account any unmanned vehicle coming into it. So this is one of the first obstacles that this technology faces, which is getting access into the real tracks. Another of the challenges, the big challenges that we face with this is positioning, navigation, location, and being able to accurately position the payload where the job is required. This is primarily because it's a complex and dynamic environment. The robot needs to understand what's around it and being able to deal with obstacles and people and other network assets too. Another of the difficulties with this is the fact that some of these faults that we wanted to monitor and to inspect may be in the centimeter scale, possibly a number of them being too small together. We understand that there are thresholds in network rail inspection methodology, so also these need to be taken into account to be able to come up with an acceptable resolution for location. There are many layers, there will be several layers, about how to accomplish this location using absolute and relative layers of positioning. So for payload positioning, we have several effects in there. We have a number of error sources that affect payload positioning, and these need to be characterized and compensated for. What would happen is that if we don't deal with this, then we would not be able to control where the repair would take place. So it's important to deal with them and acknowledge where these error sources come from. We understand so far that some will come from wear on the wheels, their own vehicle, the dynamic response, the trolley that might need to be put in between the trolley and the vehicle and the track, control execution, etc. So I'm going to play hopefully I can play a little video here that shows some of the vehicle dynamics that we have to deal with. So I understand that the video is playing. I cannot see it here. So I'm going to do it again so you can see that moves very abruptly, and that needs to be controlled as well. I'll move on. I understand the video. So I mentioned earlier on that that the vehicle, the width of the vehicle is just about the same size of the track gauge. So obviously we'll not be able to make the vehicle run on top of the track without being a very rough ride. So we need to place a trolley in between to enable us to position our inspection methods. The trolley, the workhorse itself comes with cameras and lidars, but we may need other inspection methods that we need to position for this. And the best way to do this will be on the trolley rather than on the vehicle. So there will be some issues with this. One of them is braking. We we understand, we know that these trolleys can run away if they're not, if there's if the inertial effects are not controlled properly. There is some issues, or there could be some issues with regards to loading or unloading of the vehicle in the trolley. So we need to devise our own procedures for this, and also the trolley will affect positioning. So not only location, but also where do we put the access points for these trolleys needs to be considered. And also there are some issues with handling because it could be heavy, so they need to be taken into account as well. So as I said, we expect to be able to deploy other technologies in there like ultrasonics, maybe thermography. But these could be the issues for the deployment of this type of vehicle. So I have here another video that I wanted to show. It's possible they won't play, but I want to describe what we were doing with this. We work as part of the same projects on a demonstrator to being able to try and detect rail foot defects. Now, rail foot defects are those defects that happened on the bottom of the rail. They're very difficult to detect. They can be critical defects too, which can lead to accidents if they're not detected on time. So, so it's quite hard. This is actually a very hard defect to detect. One of the ways to do this, we attempted to do this, is using thermography, and we had a demonstrator where we put a thermography camera at the end of a robotic arm, so that the camera could scan a rail sample with a number of simulated defects machined at the bottom of it. There was some success in this, where we were able to detect relatively large defects at the bottom of it, inspecting from the side of the rail sample. I would assume this video won't play, but let's have a look. So I don't see it playing, possibly it's not playing, but I wanted to illustrate the type of defects that we were able to detect. So the green one is a rail foot defect, which has a diameter of, I think, 20 millimeters, and it's placed under the track, the rail sample. And the one that looks orange in here is a simulated crack placed on the rail head, top of the rail also. So we've done some investigations with thermography at the end of a robotic arm in preparation for this phase of the project. There were also more demonstrations at Cranfield, and what to do, for example, with cobots. And one of our students recently demonstrated or built a small device to demonstrate how robots could interact with people. And again, the robot is able to navigate interaction or obstacles placed by people in there. So again, it's a demonstration of technology. Unfortunately, my videos are not playing for this presentation. We will not be able to see it today. I'm just going to describe briefly the Autonom project. And this is a project that was sponsored by primarily EPSRC. Our main industrial partner in this was Network Rail. So here in the Autonom project, we were looking to develop a methodology, an architecture to being able to optimize maintenance, and that involve technical triggers, planning and scheduling, and developing technologies to best optimize the routines for maintenance, the calls for maintenance, which involve cost effectiveness. I think I can cover this on the next slide with more detail. So we developed for this also a demonstrator, and in this demonstrator we had a number of assets. We limited this to 10 assets, which were here, represented here in this green area. These also put a video here. Maybe you will play it. Let's see. No. So this is the interface with human, and it will show here the 10 assets in green. When we click these buttons here, then it runs the scenario, and when it runs scenario, it loads a data set of rail inspections, and it does some analysis on them to be able to plot degradation of these assets. When these assets then reach a certain threshold, the lights here will turn from green to yellow or red, depending on the condition of the asset. And at that point, is able to schedule maintenance. So what we do now is, in this, to demonstrate this, I can't do it because it's not playing. But then I will move into the scheduling tab, and in the scheduling tab, again, we load a data set with jobs that are related to the asset monitoring that we have on this screen. At that point, it does analysis of the several tasks that need to be done and prioritizes them in using heuristics and a genetic algorithm. It does take into account cost monitoring. So for this, we also have to work with data sets for cost, understand where the cost drivers that drive cost up in terms of the maintenance. For rail infrastructure, a critical part of this is an idle service when trains do not run because there is a failure of the track. This is the most critical cost driver for them. So we didn't know that. We learned this through this research. Eventually, what the system does, or this demonstration does, it gives you a schedule of maintenance based on the number of crews, which is then deemed to be the most effective way to do maintenance. I just wanted to say, I apologize for this. I don't know exactly what happened. I just wanted to say that this presentation had many contributions from staff at Cranfield Network Rail, the Catapult Connected Places, and I just wanted to thank you all for your patience, and I'm happy to respond to any questions.
Hi Isidro, thank you for that. That was really, really good, and thanks for managing to press on despite the few technical difficulties we had. So I do have a question here from Robert Cummins. Thanks for that, Robert. So the question is this likely to replace Network Rail's measurement fleet in the future? And if so, how many years might it be to be ready to be able to measure the whole network?
Thank you for the question. I think my understanding of this is that this is not meant to do, at least on the first stage of this, this is not meant to replace the new measuring train. It's at this stage primarily targeting specific jobs that are difficult to do. We understand that, or we know that the network, the new measuring train goes at certain speed, very high speed, and does take data of the track quality of the track is recorded, and then if degradation is detected, then alarm is raised. But these systems, what happens later is that after the new measuring train raises an alarm and sends a job to someone to do the job, someone else has got to come and do it. And the purpose of the system, the rail inspection system, is to actually respond to jobs that are already scheduled, and so especially those that involve hazardous areas or working at night. It's not meant to run as fast as the new measuring train, because the maximum speed that this vehicle does is 18 kilometers per hour. So it's not expected to do that, but instead it's expected to tackle specific jobs a lot of these places that otherwise would be done by people in the middle of the land. As to how far this is, we work in a technology readiness level 7. This will take about a couple of years to finish, and then the following technology readiness level need to be commissioned. But those will be more related towards supply chain and actually getting a real product or a product from the supply chain, and then do final tests in the network. So I'm not too sure this will be too soon, possibly 2 or 3 years time if things were progressing to plan.
Brilliant. No, thanks for that. So I'm keeping an eye on the chat, and it looks like that's the final question. So what I will do is I will give I'll try and give a virtual vote of thanks for those of you that come along to our events, know that we talk about future events and give a vote of thanks. So I'll try and do that virtually. So yeah, Simon and Isidro, I wanted to thank you both for coming along. It was really, really interesting. I mean, it was an area that I didn't know a huge amount about. So, I mean, one thing that really struck me from Simon's part of the presentation was how much the passenger equates maintenance with the cleanliness of the train. I thought that was really, really interesting and something that you don't really think about. So, yeah, that was a really interesting point, and also the RAS concept, being able to reduce the fuel service times from 30 to 7 minutes. I mean, wow, that's a huge reduction. And also when you consider the number of vehicles in the fleet and you start doing the multiplication, I mean, it's a huge amount of time saved. And with Isidro, it was really useful it was really great just to see how the robot at Cranfield is evolving and how the technology is evolving. It was really interesting to see, for example, just how things such as the payload positioning has an effect, and the requirement for a trolley, and just all of those things that you wouldn't really think of necessarily with this sort of project. But when you start to get into the detail, there's loads of small things that do add up to become really a very, very complicated problem indeed. So it was really interesting to hear how you're working through that. So yeah, I'd like to thank you both. What I will do, whilst I've still got everyone on the line, is remind everyone that we do have an event next week as well, on the 23rd of September. So that will be kicking off at 5:30, and we'll be ending at 7. That is a 3-speaker event, and it's hydrogen trains and their place in decarbonising the railway. So we'll be talking a little bit about hydrogen trains and the development that's going on in that area, and then we're going to be talking about decarbonisation as a whole. So another really, really relevant and present, up-to-date presentation. So I hope you can join us for that. But all that it leaves me to say for today is thank you very much again to Isidro and Simon, and thank you very much to you all for coming along. Thanks for bearing with us. We did have a few technological glitches along the way, so thanks for sticking with us. I hope you managed to enjoy the presentation and find it useful nonetheless. And yeah, hopefully see you soon and speak to you all soon. Thanks.